All right, this continues our lecture on confidence intervals when sigma is known. So what we're looking at is the last example that I was finishing up. So we had found our margin of error, and in order to find an interval for the true population mean, we need to add or subtract this margin of error to x bar. So our x bar was 64.3, and I'm going to add and then also subtract 6.57. I'm going to go one decimal more than the original value here, and then I'm going to round it back to the one decimal value. So what I found, 64.3 minus 6.57 was going to be approximately 57.7, and 64.3 plus 6.57 is going to be approximately 70.9. And this interval here, and you'll notice interval notation, this interval is an interval that we would expect to contain the true population mean 95% of the time. In other words, when I would build 100 such intervals based upon this sample, I would expect 95 out of 100 such intervals created to actually contain the true mean of the population. Does it mean it's in there? No, not at all. The mean may not be in there at all, but I expect 95 such intervals to contain the true mean. And that is a lot better than saying, yep, here's a point estimate, 64.3. It's either the value or it's not. You just get a 50-50 shot. So this is a far superior estimate of the true population mean. So remember that what this interval represents is an estimate of the mean. So it's a value where values of the mean could possibly lie. So estimate of mu. And I'm going to highlight that right like that. All right. So now we're going to do another example. So our second example says the axial loads of 175 cans have a sample mean of 267.1 pounds and population standard deviation of 22.1 pounds. Find a 99% confidence interval for the population mean. Okay, so first thing, we have to decide on n, then we have to decide on x bar, and then we have to write down sigma. And then we'll have to go find our critical values based upon the confidence interval or confidence level. So what we first have is, what is n? What do you think n is? Well, n is the 175 cans. And then we need x bar. Well, that's the sample mean. X bar is the sample mean. That's 267.1 pounds. And then we need sigma. Now sigma, it has to be the population standard deviation. So this is 22.1 pounds. And then the confidence level that we want is a 99% this time around. So this is 0.99. Remember, that's what goes in here in the middle. And that means that we have over here alpha over 2. So our alpha, 0.01 this time, divided by 2, or 0.005. That would be our alpha level. So, alpha over 2 levels, so 0.005 in each of these tails. And that is what we need to use the inverse normal based upon. So we're looking up the z value, the critical value, remember that's what that's called, that gives us 0.005 in the tail. So I'm going to use my t-table again. And my t-table I'm going to be looking up in the last one. And remember, I can base the t-table upon the area in one tail or two tails because I have both. So the area in one tail would be the 0.005, which is this one right here. And see, you notice in the area in both those tails is the 0.01. Remember, this is alpha divided by 2. So now if I scroll down to the very first column and I look at the large sample, that's where I find the approximate z, I'm going to find 2.576. Now if you go back up to your z table, the z table is another one of those instances where we find the stars, and the star here between this is the positive one, the negative one, the area where I find the 0.0505 and 0.495, it actually says it's negative 2575. And if we calculate it on our calculator, what we find for the calculator's value for 0.005 in the tail is going to give us negative 2576. So the one that's found in our t-table is actually more accurate than the one that's found in the z-table, because it is more closely approximate to the value that you get using the entire distribution. So we're going to use 2.576 as an approximation, but it is really typical that people use 2.575. That's the one that you see used more than any other one. So now, once we have that value, we're going to go through and we're going to calculate our margin of error. So we have 2.576, and then we're going to multiply that by the standard deviation of the population to 22.1, and then we're going to divide that by the square root of n. Now notice that n is greater than 30, so we didn't even need to know that these things were normally distributed this time around. So let me go ahead and make this calculation. And the calculation that I end up getting is that this is approximately equal to 4.3034, and then 73. And so I'm going to have my axial load here, I'm going to change colors again so we can see it more easily, is x bar, which is 267.1, and then plus or minus, and I'm going to go to the hundredths place since how this is in tenths, so this is 4.3, and that would be 0 anyway. And what I do is I take this number and add it, and then I take that number and subtract it. So 267.1 subtract 4.3 is going to give me 262.8. 262.8. And then 267.1 plus 4.3 is going to give me 271.4. And those are in pounds. And so again, interpretation, this says that I would expect the true mean of the population to lie between 262.8 and 271.4 pounds 99% of the time. So in other words, if I were to create 100 such intervals, I would expect 99 out of those 100 to contain the true population mean. Now, one of the things that you should realize that is as you get a larger and larger confidence value, so your 1 minus alpha is larger and larger, you also get a larger and larger interval. So these z's, remember, move farther and further out in here to the tails as this gets bigger and bigger. And what that means is it's moving your x values further and further out into the tails as well. So even though you have more confidence, you have a lot more value spread to which that mean could be in, which is what gives you that larger level of confidence. Okay, now let's go ahead and look at the next examples. And the next examples, we're going to be using our formula in just a slightly different manner. In this go-around, what we're going to use is the margin of error formula to find a sample size, because sometimes we know what level of confidence we want, we know the population standard deviation, and we know what tolerance we want, the margin of error, what range of values do we want to be within. So what we want to do is we want to create we want to do sampling so that we'll have the desired level of confidence. So this is what you would really be doing if you were to actually have a situation where you were going to go collect data and you were going to do that for someone yourself or someone else in order to get certain levels of confidence for them. Alrighty, so we have just basically solving this formula for e backwards so that we get to n. So you see I multiplied both sides by the square root of n, then I divided both sides by e, and then I squared both sides, and that is what gave me my margin of error formula, or my formula for n from my margin of error formula. So this is for a known alpha, a known sigma, and the margin of error being known. In other words, we're going to set it up that way. So we're going to go ahead and work this for this following example. Suppose that the weights of all fox terrier dogs are normally distributed with a population standard deviation of 2.5 kilograms. Population standard deviation of 2.5 kilograms. I'm going to write that down. And then I want to know how large a sample that should be taken in order to be 95% confident. So in other words, 1 minus alpha is 95%, right? And that is going to tell me that I want 0.05 out here in the tail divided by 2, or in other words, I want 0.025 in the tail. And then what the next thing says is so that the mean doesn't differ from the population mean by more than a half a kilogram. That is telling me about my margin of error. So differing from the how much I want it to be different from the mean is a half a kilogram. So I'm searching for the sample size. So just like before, the first thing I have to do is I have to find this critical value for 0.025. Now eventually you're going to get to memorize that if I want 95% confidence level for a confidence interval, I'll use 1.645. If I want a 95%, I'm going to use 1.96, and if I want a 99%, I'm going to use 2.575, or the better estimate actually being 2.576. So now let's go ahead and take a look where we can get that in the table. So remember again, if I want 0.05, oops, pardon me, this is the z. If I'm using this t-table, which is easier, remember, and I have the area in one tail, that's 0.025, and remember in two tails, 0.05. So I look down at the bottom and you see 1.96. So this critical value, and by the way, the Brace book doesn't use the z alpha over 2 that I use. The Brace book uses z sub c for a critical value. So this is plus or minus 1.96. And all we're going to do is use the positive one because we don't care about the negative one. It's going to be squared out and it's going to be the same anyway, right? So we have 1.96 times 2.5, and then we're going to divide by 0.5. So that's what we're going to be getting for our value. So I'm going to go ahead and I'm going to multiply that 1.96 times 2.5, and I'm going to divide it by 0.5, and then I'm going to square it, and I get 96.04. Now 96.04, this of course is not an exact number, but if I want to know how many to use, I'm always going to go up from that because I want to have at least my level of confidence, right? So I would be using at least 96. Or excuse me, 97. So approximately 97 to do that computation with. But in actuality, probably what would happen is you'd use 100, and that would give you a slightly larger value for your confidence level, but it would give you at least that, and that's what we're after. Alright, so I'm going to let you look at the next one and do that one on your own, and you should be seeing out of this one a 2-inch margin of error and 90% confidence, and the height of men and women, that was, the height for men, that was a standard deviation of 2.5. Alright, that ends this video.